Okay, I'm going to do an example, you guys, a linear algebra example from section 1.8, which is dealing with, we start talking about linear transformations. By the way, we didn't give a definition of a linear transformation, so that can happen in class. But basically, it's got a certain property, otherwise it's not a linear transformation. So let's read what we've got here. We've got matrix A is equal to that matrix, and then define T of X to be a linear transformation. I guess I will. A linear transformation has the two properties. T is a linear transformation. Okay, it's interesting because it's going to transform. Basically, what we talked about in class is it's going to take vectors from, say, one R space, R4 or whatever it is, and map it to R3 or 2 or R4 again. The linear transformation has two properties. It doesn't do anything to it. It doesn't stretch or make it mutate or anything like that. Those are fun. But instead what you have are these properties. Number one, T of vectors, say, V plus vector U is equal to T of vector V plus T of vector U. Okay, one. So the addition is preserved, so to speak. The transformation of the sum is equal to the sum of the transformations in the new space. And then also scaling is preserved. So if I take T times some scalar times V, it's equal to C times the transformation of V, like so. So the scaling is preserved in the new space as well. So that's what we call a linear transformation. If you do other things to it, if they're not preserved, if something else happens, we might have another name for that. Okay, I was talking about spaces, and I was saying, okay, it maps from R3 or whatever. Let's nail that down. So say we've got this definition going at us right here. We've got T is equal to, it's defined as a matrix times a vector. And by the way, all matrix transformations are linear. I don't know if I'm saying that right, but what I mean by that, okay, is that when you multiply a vector by a matrix, that's always going to be linear no matter what. Okay, so what's going on here? If we say T of X, which is equal to A times X, and it turns out to be, it maps to some other vector. We've done this in class before, but the game you can play immediately is you go, well, the size of our matrix, if you look up here, it looks like it's a 3 by 4. So whatever vector it multiplies with, remember, this 4 has to equal his 4. That is, the columns in the matrix have to match the elements in the vector. So it has to be a 4 by 1. And remember the other part? If you put these two numbers together, what it gives is the size of the product, which is 3 by 1. So X is an element of R4 because he's 4 by 1, and B is an element of R3, which is, he's a 3 by 1, and X is in the domain, okay? So the domain is simply R4, and the codomain is R3. So this particular transformation where A is a 3 by 4 is going to grab, so to speak, multiply with 4 tuples, and the product over there on the other side is going to be a 3 tuple, an ordered triple, okay? By the way, the word range is used only for what we call the image of A, the product of A with all the vectors. So what's the span, if you will, of the product of, what's the span really of the columns of A? That's a good way to say it. The span of the columns of A is called the range. Now you may not map all the way through. Oh, that's a couple questions I have to add on to this thing. So let's get going with this stuff. Okay, we'll get there. All right, so what is the image, okay, of this vector? This is an example. So X is negative 3, 2, 0, 8. What's the image of this vector under this transformation? Well, now, because I called it X doesn't mean anything. It's the language. The image of this guy under this trend. Okay, so he's in the domain. So all you have to do is just take down A. What you're going to do is you're going to go A times X equals. Okay, so 1, -2, 3, 2, -3, 1, -4, -6, -1, 3, -4, -2, and then times -3, etc., etc. So our vector that we're goofing with is -3, 2, 0, 8. So you very quickly do the product of that. That's what you do. The fast way of doing that product, I think, faster than writing it out as the definition, is just go row by column and row by column and row by column and see if we can do this. We know it's going to be 3 by 1. So let's see. The first one is 1 times -3 is -3, and -4 is -7, and 0 is -7, and 16 is 9. Now watch me make a mistake for posterity here. You guys are here to help me, so okay. 9 and 2 is 11, and 0 and -48. So it's a -37. And then lastly, we've got, well, that's a negative, right? Let me check, make sure. Yeah, it's a 3 and 6 is 9, -16, 9 minus 16, what you got, -7. So this is our so-called B, if you will, okay? So what I'm going to say is that X, let me change this color to this guy. So we're going to say X is an element of the domain. And B is the element of the codomain. But you see, this particular example, B is also what we call an element of the range, because we do have an X that maps to it. So if you're reachable, so to speak. And so we can also say this, B is equal to -3 times the first column, plus 2 times the second, da, da, da. What I'm really saying is that B is in the span of the columns of A. So that's where I get this idea that range is really the span of the columns of A. That's another way of saying the language. All right, this video is getting kind of long, so we'll keep going. Let me get to this guy now. All right. All right, so what set of vectors in domain T is mapped to this vector, B? If they do indeed map, let's find out. They may not. Okay, so A is again 1, -2, 3, 2. Okay, and in this case, what we're trying to do is reach over to B, which is 5, 1, 6. All right, so what we've got here is 1, -2, 3, 2. And help me out here. -3, 1, -4, -6. And then finally, we've got -1, 3, -4, -2. Like so. Okay, so to solve this, that's what you do, is you solve the thing. So I would quickly run this through an augmented matrix. And what we're really looking for is the pre-image. Okay, so 1, -2, 3 and 2, and -3 and 1, and -4 and -6, and -1, 3, -4. And I wish I had already done this, because you guys are experts at it, but here we go. I thought I was ready for this. Here you run the zeros there. So it's 3 down. So we're going 3, row 1, add row 2. We're also going to go row 1, add row 3 in all of this. Okay, so we're going to get a 0 and a 0. So we're going to go 3 down. So 3 is -6 is a -5. And 3 here is 9, and that's a 5, okay. And 3 here is 6, and -6 is 0, okay, interesting. And then 3 here is 15, and 1 more is 16, okay. Adding down the top and bottom rows is 0, 1, -1, 1, -1, 0, and 11. Okay, so some work to do here, some surprise, and we're running out of room. I should have made more room. I write too big. So 1, -2, 3, and 2, and 5. And what I'm going to do is I'm just going to, obviously, if we mess with these guys, I'm going to switch rows. And, you know, instead, I'm going to divide by, say, 5. I'm going to get 0, -1, 1, 0. And what is that? 16 over 5. And then I'm going to use the -1 and add down. So I'm going to go -1, 1. So I'm going to get 0, 0. But then I've got a -1, 1 again. So I had 1, -1, -1, 1. So what I'm doing is, with this row, I'm kind of cheating a little bit. I get a 0 and a 0. And I add this guy down, and I've got 16. Right here, we have 16/5 plus 11, which, you know, that's not a nice number. 55, 65, 71, 71 fifths, I guess. And look what we have. We have 0 is equal to 71 fifths. What does that tell us in all of this? Sorry, that's a messed up thing. I got another question I'm trying to hide from you. It tells us there's no solution. He said in consternation. Okay. Okay, so this is what we end up with. There's no solution. What does that mean? Well, you can go back up to this and go, what set of vectors? And the answer is none. B is not in the range of this transformation T. Okay. So what does that tell you about onto? What does that tell you about onto? Yeah, that's a good question. I was talking to students about that. I'll come back to that question in a second. But what we ended up when we road reduced A, we found it to be, let me write that up. We've got -1, -2, 3, 2. And I'll just look at A. We have, let's say, 0, 1, -1, 0, or yeah, 0, -1, 1, 0. And then we ended up with 0, 0, 0, 0. And what happened up there was this is a question from students all over the place. What happened is, look at that. I had a potential for a problem. There is a problem. There's no solution. So what that means down here is when we just row reduce A, we can answer stuff. Is A, well, I should say not A, but what his official name is T, does T, sorry, get the language right. Does T map, and here's the word, onto, let's call it R3. Does it map onto all of R3? Up here, we picked a guy from R3, and guess what? Nothing maps to it. So is it onto? That is to say, does it map onto every vector in R3? And the answer is it onto? No, it's not onto. It doesn't reach everywhere. How can you tell quickly? Well, you look at each row and you look to see if there's a pivot in each row. There's one there, but not here. If there's not a pivot in each row, then it's not going to map onto. That's all there is to it. Just by row reducing, you can tell with this linear transformation the nature of it. It maps onto a subset, or what we'll call a subspace later, of the actual codomain. It reaches there, but not everywhere, okay? And then another question that happens is, does T map one-to-one to, say, R3 using lousy language? That's another one that you can settle by looking at pivots, and then I'll come back and explain it. It's a longish video, apparently, but that's okay. I have a lot to say, apparently. So what I do for that one is I see the pivots, but I notice there's a couple of columns that are free. We have free variables. Watch this. So this question up here, last little demo, this question says, what vector is mapped to 0? And it says if, you know, you took AX equals 0, and you tried to solve it. Now remember, when we do that, we put over here the vector 0, 0, 0. Okay, so the augmented matrix would be the same row reduction. We'd say we would get to 1, -2, 3, 2, 0, -1, 1, 0, 0, 0, 0, 0, and guess what's over here? 0, 0, 0. There's always a solution to 0. There's always somebody, you know, who always goes there trivially? That's right. The 0 vector in the domain trivially maps to the 0 vector in the range, in the range. Okay. Now, but in this case, you notice, look at this. I've got two basic variables, call them x1 and x2, and then I've got x3 and x4 are free. Okay, so if we were to go ahead and solve this like we're supposed to, well, okay, let's do that. What we would say is that minus x2, okay, plus x3 is equal to 0. So these two, x2 and x3, for this solution have to be equal. But then you have the top one as well. You have x1 minus twice x2, but x2, remember, is x3. Then you have plus 3x3, and plus 2x4 is 0. So what you end up with is x1 is equal to, let's see, 1x3, so negative x3, and minus 2x4. So very quickly, I can tell you the answer. If you want to keep doing this, x1 is minus x3 minus 2x4, x2 is x3, x3 is itself, it's free, x4 is itself. These two are free variables, but when you write it in vector form, which is nice, you end up with x3, take out the coefficients, x4 plus x4, take out the coefficients, so it's -1, 1, 1, and 0, and -2, and 0, 0, and 4, -2, 0, 0, and 4. Okay, so that's the actual solution. All infinite number of these vectors map to 0. So does it map 1 to 1? That is, does 1x always map to 1y, so to speak, or does 1x in R4 map to only 1x, 1b in R3? The answer is no. 0, 0, 0 is a b in R3, and we have an infinite number of them. So the way you can tell is if you get free variables when you reduce, it's not 1 to 1. So you could say, does it map 1 to 1? No. And I would say, ooh, I'm running out of battery. Sorry, and your patience too, I'm sure. But what this means is that if you have not every row has a pivot, that way you know it's not onto. And no here, let's see, how'd I go? There are, well, one way to say it is, a better way to say it, not every column has a pivot. Not every column of A has a pivot. So this is a long one for this section. I tried to do too much, didn't I? Well, anyway, hopefully it explains a lot, and I hope you get something out of it. And we'll see you in section 1.9 where we're going to do some other stuff.